But before we do the chart, again, let's review why do we care? Well, again, they tend to align when they're placed in an electric field. So the positive of the molecules is oriented towards the negative plate and the negative towards the positive plate. You can use an electrically charged object to attract polar molecules. Like if you have a mixture, you could like use an electrically charged magnet to separate them out. You also have this situation where they provide structure for certain liquids. They'll line up positive and negative, and it affects the properties. Like it affects viscosity, it affects melting point, volume, it affects all kinds of properties. Then we have polar liquids. They are better at dissolving polar substances. Non-polar liquids are better at dissolving non-polar substances. Like dissolves like. So ionic things are like an extreme polar. So any kind of like sodium chloride or any kind of salt is usually pretty soluble in water. And with this non-polar thing, I actually recently had someone talking about this fingernail polish remover. So fingernail polish it's an organic molecule, and it can be dissolved with ethyl acetate. That's fingernail polish remover. But there are plenty of things that are similar to ethyl acetate that also will dissolve fingernail polish. And they're similar, and they also are the same amount of polarity. Lastly, ionic compounds can dissolve into polar liquids like salts. And you may just find this is just useful info. You don't have to use this. So just some useful tips there. Let's look at our chart. Don't forget the learning objectives. Also, you can go back and review. Make sure you understand what's going on. So we're looking to see if something is polar. So the idea is with these shapes, and we're going to understand the shapes a lot better when we get into electron geometry and molecular geometry. So we are going to be understanding these shapes more. But for now, since we're not quite there, we just need to know the idea of looking at the bonds themselves. And then we're going to come back and we're going to, once we understand these shapes, we're going to fill in this column. But I'm going to go ahead and I'm going to draw the arrows. So HH, they're the same atom, so there would be no arrow. Beryllium's like on the left side of the chart, and the chlorines are on the right. Beryllium to all of these chlorines. Again, these arrows will mean more to us when we get into the shapes in the next chapter. So I'm going to draw these arrows like this. This one especially is very tricky. I know that this looks flat. I'm going to make a little note that this is not flat, even though it might seem like it is. And then over here, this bond here, yeah, we're definitely going in all of these different directions. So chlorines, fluorines, and halogens, most likely those are going to be the most electronegative, but just do a quick check and a quick count on that. Again, oxygen is more electronegative than hydrogen. So again, we are just drawing bond dipoles. We need a little bit more information before we can decide if the overall molecule is polar. But I kind of gave some hints. You can probably go back and read that last little reminder section, and you might be able to make some guesses about the polarity. But I'm going to draw our little bonds. So for this point in the chapter, you just need to be able to identify if a bond is polar. And you also need to be able to identify which bonds are more polar than other bonds. So the larger their electronegativity difference, the larger the bond. Notice that chlorine is pretty electronegative, but fluorine is more electronegative. So comparatively, we draw the chlorine as being positive. This one's pretty tricky, except that anything compared to fluorine is going to be positive. It's just known as pretty neutral-ish. Again, the fluorine, if you got fluorine, those arrows are going out towards the fluorine. So hopefully you're getting an idea of how to do this. You just have to look on the chart. You kind of look where things are. Notice that xenon is not even on the electronegativity scale. Like that's how low its electronegativity is. So we don't hardly even have to mess with him. worry, like anything attached to him, the other thing is going to be electronegative. So you have a few more of these. Go ahead and try drawing your own arrows in, and I'll go through and I'll review it. And if there's no difference, then don't draw anything. Most of them will have something different about them. And then we'll come back to it.